Yeah, kind of sparse this one. I guess week 3. So. Okay, a few things since we're through the first 2 weeks. I just want to mention this before we move on into the material. You should have turned in homework 1 and 2, lab 1 and 2. Those should be done by now. You got them in by last Friday. I graded them and I posted grades. So you have full grades up there. 20 points each. So that's 80 points you should be looking at. So, I mean, realistically, that's like a lot of points. But I'll just remind you, there's 80 points per week, 40 points per week, and it just builds up. Stay up with it. If you miss something, get it in. If you missed the lab and weren't done with last week's lab, ideally you would have gotten in yesterday and finished it up so you're ready to go today. You can always contact me through Blackboard if you have questions. It has an equation editor even, so if it's a mathematical problem, you're welcome to use it. But I can use it too. I'm pretty fast at it since I use it. I won't use it if I don't need to, so faster. But just in the keep up material. So this week is week 3. I already asked. You might look in the meantime. Has a very famous name. Have you ever heard of Ohm's law before? I know. This is the foundation of everything in electricity. Its importance cannot be overstated, and it does not go away. Ohm's law will be relevant today. It'll be relevant when we're a semester down the road. At the end, it'll be relevant no matter what you ever do in electricity. So what it says at its base, and this is more of a scientific definition, but I'll give you, it directly relates to the others. The resistance to the current is equal to voltage divided by the current. Okay, this is more of a physics definition, but I'll give it to you because that is what the definition is. The definition says if I went into something, look a little common. I'll come back to this part for an ohmic material. Okay. What this says, if I went to the lab and I sat down, I took my voltmeter I now know how to use, and I measured the voltage, and then I take my adjust it to do current and measure my current. That's my ammeter. The resistance of that material, by definition, is equal to the measured voltage over the measured current. For an ohmic material, I'm just going to say an ohmic material, this seems a little bit circular, is something that follows Ohm's law. But ohmic materials are conductors, resistors, pretty much everything we're going to use in here the first few weeks, Ohm's law applies to. So, things like when we get to transistors, they're not ohmic materials. They don't follow Ohm's law, but we actually use an application that looks a lot like it. We get AC circuits, we'll do some stuff with capacitors and inductors. I know these are all terms that you may or may not have even heard of before, but they're electronic components. All right, Ohm's law. Now, the way we usually use this is a little bitty, it's an algebraic equation where R is the resistance. So R is the resistance in ohms. V is my voltage in volts. And I is my current in amps. Now, I can do some algebra here and solve this, and I will see that the way I would normally use it is if I know the voltage and I know the resistance of something, I can find the current by taking voltage over the resistance. Or if I know the current I can multiply the current times resistance to find the voltage. These three are just identical algebraic equations. If you're comfortable with your algebra, I would just write one down and keep it around all the time. You're welcome to write all three down. You'll also see out in this week's folder as a handy little triangle. This is really common to see in areas where you do electronics. So if you need current, that's voltage over resistance. If you need resistance, that's voltage over current. If you need voltage, that's current times resistance. So if they're on the same level, they multiply. If one's over the other, you divide. I don't care which you use. All I care is that you can do it. There is also a circle you will see in that same section that has voltage, current, resistance, and it has power on there, which I haven't talked about yet. And it has the relationship equations between all those. If you have two of them, how do I get the other one? It has a whole series of equations to pull from, and it's just like a big circle cut up like a pie chart. You're welcome to go grab it and use it all you want. It just I won't draw it up here for one. It's a lot to draw, but for the other half of it we haven't talked about. But you can use it for also. Okay, this equation is the foundation for everything we're going to do. Units. Your units are critical. I graded stuff last week. Most of you did pretty well. A reminder, a number without a unit is pointless. You might as well leave it blank. Like I said, you write down a number. I don't know. It's a miles per hour. It's years. It's just a number. It's a number. We're not a math class. I don't care about numbers. I care about measurements of the real world phenomena. Likewise, I do know these are new to us. Your equipment gives you numbers. I need you to start thinking about, I have a prefix that's a milliamp. Most things we're going to cover in here are milliamps. A milliamp is 1,000th of an amp. The difference is really important, okay? It's like an inch versus a mile. No, they're both measurements of length, but they don't really mean the same thing. I know they're new to you. I'll just give you a heads up here. If you're talking amps, it's not going to happen in here because our boards would be turned into smoke by amps flowing through. And you wouldn't be on the floor if amps are flowing through you. It would be down to the EMTs. Milliamps, though, you're good. Low milliamps. High milliamps are great because they eventually become amps. Watch for those. If you do a homework calculation and you end up with amps, make sure you go back and check it. Now I do that in some because we're gonna have, there's no reason with the numbers there I can't get everything's in amps, and everything we have covers power. But just watch those. You can also have millivolts and volts. Most things we'll look at will actually be volts, but we'll look at millivolts plenty. So I do realize that that whole milli, it's like millimeter to meter, and we'll talk a little more about it. But watch those. Okay, so I have two things that you need to be the unit, and you also need the correct multiple out front. Milli, micro, all that. Okay. I'm going to erase it and move on back to my Ohm's law. I just kind of, we're hitting these, and one's like, yeah, let's emphasize this. All right, so let's just try this, and we're going to use it in a couple of examples. So I'm going to draw my schematic here. The ones we've drawn so far, and just before you draw this with me, I'll go ahead and write it down, then I'll draw the next one. Ones we've drawn so far, we tend to show a battery. So we hooked up a 6-volt battery, and we hooked it up to a light bulb. Lab 1, you did that. And you measured the current that went through that light bulb. Anybody remember what kind of current you got? This is actually a pretty decent current because it was lighting this light bulb up. I think it was somewhere around 120 milliamps. It takes a lot to go through light bulbs. Old light bulbs to put that light that tungsten filament up. So we use the modern LED ones, right? So a lot less current, a lot less power, a lot less cost. Find the resistance of my light bulb. Okay. Technically, light bulbs aren't only materials, but let's ignore use our past example to do a calculation with our new equation. Resistance equals voltage over current. Your voltage was 6 volts. You measure from here to here, it'll be the same as here. Your current's 120 milliamps. If I would like to do the calculation, I need that in amps. That'd be 6 volts. Move 1, 2, 3 decimal points. That's 0.12 amps. So I'm going to take 6 divided by 0.12. To encourage people to work with me. I know how to run the calculator. These basic division ones aren't too bad, but I think I know it before. As you go through this, I would have your calculators out and work with me. My example I always use this from years of coaching. Not having your calculator out working with me is like watching me shoot free throws and assuming you can do it. That doesn't make any sense. You have to do the work. I know how to do it. Basic division, multiplication, you got down. I got it. But once we start doing the powers and stuff, because one of the things I'll find is a lot of times I'll get to like second semester and all of a sudden most people can't get the numbers in now the calculator correctly. It's kind of silly. And you can fit it all out if you're working with me. All right, everybody good with that? 50 ohms? Okay. I'm going to use this as an example. I said this is not really my ohmic material. Why? Any ideas? Light bulbs aren't ohmic. The reason is because as I change the voltage, the actual resistance will change with it. So an ohmic material holds its voltage. It always keeps that proportion between voltage and current the same. Light bulbs will have a different resistance to go up and down. But for doing a calculation at one spot, works fine. It just won't be 50 ohms if I hook 12 volts on. All right, what is an ohmic material? Well, a resistor is. What's a resistor? Something with a set resistance. That's what it is. So I could come in here and let's pick a simple number. 100, what are my units? Ohms. Yeah, it could be kiloohms, but I'll make this one ohms. I'll make it so we don't need to use an multiple on my first example. 100 ohms. Excuse me. So I know voltage and current, I mean voltage and resistance. If I want to find the current. Current equals voltage over resistance. Six volts divided by 100 ohms. So what's 6 over 100? 0.06 units. Amps. If I want to write it in milliamps, I'm going to move my decimal 3 spots. 1, 2, 3. So I actually need to add another 0 out there, right? 60 milliamps. 0.06 amps is correct. Why did I write 60 milliamps?
Because we're not going to deal with amps.
No, the reason I write it is this takes 4 characters, that takes 5 characters. Engineers do things as fast and efficiently as possible. We use milliamps because it's faster and easier to deal with than amps. We use kiloohms instead of using thousands of ohms because it's faster than writing 3 zeros on the time. We'll use pico when we get later on because it's really hard to write 12 zeros after the decimal point. Keep track of where you are. Don't worry about it. That's like week 7, 8. So, okay. This symbol is my resistor. Something like that. So my resistor is an object that has a set resistance. And we actually have physical resistors. We're going to talk about that end of today or Thursday. See, let's try this. So I have a circuit where I don't know the battery, but I measure current. And I'm going to stick with my 100 ohm resistor. And my current is 15 milliamps. Find the voltage. Voltage equals current times resistance. Current times resistance, current times resistance. My current is 15 milliamps. Resistance is 100 ohms. First thing I'll do is convert milliamps to amps. So move my decimal 1, 2, 3 spots. I don't even need my calculator, right? So I'm going to multiply by 100 with my decimal. Too bad. So now I've got 3 examples of using Ohm's law to find resistance with voltage and current, find current with voltage and resistance, or find voltage with current and resistance. If you can do these, that's all Ohm's law ever does. Where most of our problems will come up later on as we use it to calculate one thing, and then we can move a little further and calculate something else.